All right, guys, so what we're going to be looking at here is we're going to be going over the review for test 3. Now, this is actually just the video for the first part of test 3. There will be a second part that we're going to look over in the next video, but just be aware this is only for the first part, not for the second part, so there will be a separate video for that. The other thing that I am going to do is, for the most part, the derivatives, I've already worked them out, and I'll talk about a lot of them, but I'm not going to write them out as I go through them. So this will sort of be like an answer key as well as how to do some of the problems. All of the implicit differentiation problems I have not worked out yet, but all the other ones I have, and you'll see that as we work through this, okay? So let's just go ahead and take a look at what we got going here. So when I want to find derivatives, again, a couple things that I want to call your attention to. Like on number 1, again, this is not sine times 4x plus 1. This is the sine of 4x plus 1. So when I take the derivative, the 4x plus 1 is what's on the inside. That's why it doesn't change when I write my derivative down. So I got cosine of 4x plus 1 times 4 is that derivative. About the only other thing I kind of want to point out, this is not something you're necessarily going to have to remember, but the derivative of secant of x is secant x tangent x. So when I take the derivative, but it's not just x inside of the parentheses, everywhere that x would have gone, I have to put what was inside of the parentheses. That's why that goes to 2 places. We discussed that briefly about the secant of x when we were using the chain rule, but I just wanted to reiterate that fact right now. Then on number 3, very straightforward chain rule. Okay? The other thing I want to point out here is, like on 4 especially, when I look at 4, I realize that the tangent to the third of x is really tangent of x to the third power. So when I take the derivative of that, I have to take the 3 and bring it down first, then go tangent squared of x, because that's taking the derivative of the outside. Then I multiply by the derivative of the tangent, which is secant squared. That's where the secant squared on the end comes from. Then we repeat the exact same thing with cotangent. I guess probably we should have some parentheses around that, but not a big deal. Number 5, hopefully you can see, is a pretty straightforward chain rule problem while we are doing a product rule. And then number 6, again, kind of the same thing as what happened on number 4. The difference there is we've got 3x plus 5 in parentheses, so there's 1 additional multiplied by 3 at the end. And like I've said before, anytime you're watching these videos, if you want to check your work, obviously it makes sense to just pause the video on any screen so you can check what you have for your answers. Okay? What I do want to look at real quick, and I do want you, first of all, to cross off number 8. There'd never be anything that difficult on the AP test, so we're not going to worry about it here either. But let's say I wanted to find dy dx, but I've got x's and y's mixed together. Remember what we do, there are just a couple steps, and both of these are pretty easy ones. So I would have like 2x minus 4y to the third. Anytime we take the derivative of something with a y in it, we write dy dx after it. One of the biggest mistakes that I see when we're looking at implicit differentiation is people forget, especially when it's just equal to a whole number and nothing else, that the derivative of any number is 0. So I would have all of that is equal to 0, not equal to 14. Too many times that I see people doing these problems, they do that and they forget to change the derivative of 14, or they forget to take the derivative of 14 and they leave it, which gives them the wrong answer. Once I do this, then once I take the derivative, what we do is we isolate all the terms that have dy dx on usually the left-hand side, but you can do either side that you want. And every other term over to the right-hand side. In this case, there's only one term, so I'm going to divide by negative 4y to the third. And you don't have to simplify if you don't want to, but that is what dy dx would equal in this problem. So I got negative 2x divided by negative 4y to the third. Or if you simplify that down, you could have that as x over 2y to the third, and that's fine as well. Now I wanted to look at number 9 just real quick here, because when I take the derivative of that, I take the derivative of every term in implicit differentiation, so I get 1 equals the derivative of any trig function, the y stays inside. So derivative of secant is secant y tangent y. And then afterwards, we write dy dx. Now in this problem, again, the dy dx is real easy to get all by itself. I just divide by secant y tangent y. And I get that that is what dy dx is. And I'm all done. That is my answer to this question, which I know it seems a little bit easy. Chances are you'd see something like that on AP exam, nothing more difficult, although it probably wouldn't have secant in it. It would probably have something like sine or cosine instead. The key here again is when you take the derivative, the y has to stay initially, so it's not secant. Like if it was sine, if I wanted to take the derivative of sine of y, it would be cosine of y dy dx, not cosine of dy dx. You don't do both of them at the same time, so that's not what that turns out to be. Okay? So here's another one. Find the slope. We realize in this problem that 2x squared and y squared are multiplying each other, which means I have to use the product rule. So I go 2x squared times 2y dy dx. Plus, and again, I know that I'm doing this because I want to find the slope of the tangent line. Another name for the slope of the tangent line is the derivative. Okay, so I'm taking the derivative of this. I'm taking it one term at a time. And the first term here, I have to use the product rule. So I've got that. And then second step, I want to get every term that has dy dx in it by itself. So I get negative y squared times 4x is equal to 2x squared times 2y dy dx. Then what I do is I would just divide both sides by 2x squared times 2y. So I divide both sides by 2x squared times 2y. You do not need to simplify down if you don't want to, because that is what dy dx would be equal to. You can leave your answer like that. If you simplify it down to negative y over x, I mean, it looks better, but it doesn't mean anything different than what we had previously. So that is our answer on number 10. Now, number 11, notice it wants the second derivative. So I'm going to go 2y dy dx is equal to 3x squared minus 1. Then to get the dy dx by itself, I just divide by the 2y, so I get 3x squared minus 1, all divided by 2y. That's my first derivative. But this wants the second derivative. So what I do is I take the derivative of what I just found, and to do that, I'm going to have to use the quotient rule. So quotient rule says write down the bottom, multiplied by the derivative of what's up top, minus what's on top, times the derivative of what is on the bottom. So I get 2 dy dx all over the bottom squared. So that's all over the bottom squared. Now remember, the last step when we're finding the second derivative is that is correct, and I don't have to isolate anything like we do on the other implicit questions, but I do have to take that and plug that in for dy dx. So I can't leave dy dx in my answer. I have to substitute in this case, 3x squared minus 1 divided by 2y. It makes for a horrifically awful looking problem, but that's what we do in this problem to finish it off. Okay, so that's the answer to number 11. Number 12, we also are wanting to find the second derivative. So my first derivative, I've got to do a product rule between y and x. So first times the derivative of the second, plus the second times the derivative of the first. There's my product rule. The derivative of x minus 4 is 1, plus 3y squared dy dx. And then the derivative of 3 is 0, so I don't write that last term down. Now on this one, we're actually going to have to get all the dy dx's to one side. So I'm going to have to subtract 3y squared over to the left-hand side. And everything else goes over to the right-hand side. So I've got 1 minus y, because y times 1 is just y. Then I factor, remember, that dy dx out of the function. So I get x minus 3y squared is equal to 1 minus y. Then I go dy dx is equal to 1 minus y over x minus 3y squared. So that is my first derivative. But that's not what I'm looking for here. I am looking for the second derivative. Okay, so I want to take the derivative of that. In order to do that again, I'm going to have to use the quotient rule. So my quotient rule says my bottom function squared multiplied by the derivative of the top, that is negative dy dx, minus the top, 1 minus y, times the derivative of the bottom, which is 1 minus 6y dy dx. And then we put all of that over the bottom squared. Now again, that technically is our derivative, but what we have to do to finish this off is I have to take my dy dx and plug that in to both of those places that I see dy dx. I write it out, and then I am all finished with that particular problem. And you can just draw the arrows. Remember, you don't have to rewrite it. That would take forever. So that's my second derivative. So that's the implicit differentiation section. Now the rest of these we're going to go through again kind of quickly just because there's a lot of repeated ideas. Like here, we're looking at inverse trig derivatives. I know that they're inverse trig because it's being raised to the -1 power. Anytime you see a function being raised to the -1 power, that is inverse trig. So don't forget, you just have to have the formula memorized, then whatever's in the parentheses gets squared down here. Then we multiply by the derivative of what's in the parentheses. That's what each of those different things off to the side are. Those parentheses are not on the bottom of the fraction. Instead, those are off to the side. Or if you wanted to, you could write it up top. So on this problem, for example, I could have -2x over the square root of 1 minus x squared squared. And that answer is totally fine as well. The other two are on there. Just take a look again. The ideas are very similar here, so I'm not going to spend time talking about every one of those problems. On number 16, and this doesn't happen very often on the AP test, but we need to realize that the square root of 2 is just a number. Since that is just a number, I treat that like the power rule. I bring the square root of 2 down in front, even though it looks weird. Then I multiply by x to the square root of 2 minus 1. And that's all I do on that problem. On this one, I've got a chain rule going on, so I bring the 4 down, leave the inside alone. Then we remember the derivative of the ln of anything is 1 divided by the anything. If it's the ln of x, then it's just 1 divided by x. So on 18, when I take the derivative of that, I get 1 divided by x to the 4th minus secant of x. Then I multiply all of that by the derivative of what is on the inside of the natural logarithm. Okay, again, hopefully that kind of makes sense. I'm not going to spend too much time talking about these because I think you guys kind of have those down. I should probably have parentheses around that rather than just writing it the way that I did. Again, here on number 19, we just have to realize that we have a product rule between e to the x and the ln of x. So that's why there's extra stuff in there. Don't forget, e's and ln's follow the product rule just like everything else does. On number 20, what we're using here is we are using the chain rule, where remember the derivative of e to the x is just e to the x. If there's a number out front, it stays the same. But what I do have to do is I have to multiply by the derivative of what is up in the exponent. That's where this 2 comes from. And you might on the AP test see it written as 6e to the 2x plus 1. Okay, just they multiplied the constant numbers together, and they do that from time to time. On your review, don't worry about number 21. That's not something that's going to be on the test, and it's not something that's going to be on the AP exam, so don't worry about that one too much. Number 22, again, just applying the same rules that we've talked about before with exponential functions. Same on 24. Again, I'm going through these fairly quickly because we've talked about how to take these derivatives, so this is nothing that's overly shocking or that would be brand new to you. Okay? Number 25, we see that this is a product rule. E to the 3x is my first function, e to the 4x is my second function. And we just did it that way. You could do it another way if you wanted to, but I'm not going to discuss rules of exponents because that does get a little bit confusing. 26, we just use the power rule there to find out what that derivative is. 27, you'll notice, again, is the ln of the ln of 5x, so I had to go 1 divided by whatever I'm taking the ln of. Then I multiply that by the derivative of the ln of 5x. So it's like a chain rule inside of a chain rule. The derivative of ln of 5x is 1 divided by 5x, and then we have to multiply by what we took the ln of, the derivative of that, so that's where that 5 comes from. 28, we've got a product rule between e to the 6x and negative sine of x, and cosine of x. So that's where that comes from. Again, if you have any questions, there's a chain rule being applied there, but know that we use the product rule overall. Number 29, you'll notice is e to the, we've got a whole bunch of stuff up there. So what we had to do is we just copy down the e part, then we multiply by the derivative of what is in the exponent. And to take that derivative here, what we have to do is we have to multiply it by using the product rule, because those two things are multiplying together. Lastly, on number 30, what we have to realize is e to the third, even though it looks like an e function, e to the third is just a number. So when I take the derivative of x to the e to the third, I bring the e to the third down in front, just like I would with any constant number. Then I just subtract 1 from that number to find out what my new exponent is going to be. So this first worksheet, what we focused on mostly is taking derivatives using the chain rule of exponential functions, logarithmic functions, inverse trig functions, and just kind of how the chain rule works. We also had a implicit differentiation section that we looked at. Know that the next section, what we're going to look at is how to take the derivative when we're using velocity and particle motion problems. So that's what the next one will deal with.